Imagine you turn on the kitchen tap to fill a glass of water. The simple act of water flowing from the city main to your glass is a journey fraught with invisible resistance. Every inch of pipe the water travels, it rubs against the pipe walls, losing a tiny amount of energy. This energy loss is due to friction. It might seem insignificant for a single tap, but across a city's water supply system, a factory's chemical processing plant, the fuel lines of a jet aircraft, this friction becomes a dominant force. It dictates the size of pumps required, the pressure available at the endpoint, and the overall energy cost of operating the system. Understanding and accurately calculating these frictional losses is not just an academic exercise. It is a fundamental skill for any engineer designing a system that moves fluids. This energy loss, often called head loss, must be overcome by a pump. If the losses are underestimated, the pump selected will be too weak. The result could be a shower with a pathetic trickle of water or a manufacturing process that fails to deliver chemicals at the required rate. When a fluid moves through a pipe, it does so in one of two distinct ways. The first is known as laminar flow. Picture perfectly ordered, concentric layers. Layers sliding smoothly past one another. Fluid at the pipe wall is almost stationary due to friction. Fluid at the center moves the fastest. Movement is predictable. Movement is silent. Movement is smooth. There is no mixing between layers. This is most often seen with very viscous fluids. Example, oil. Example, syrup. Moving at low velocities through small diameter tubes, a state of calm, organized transport. The second, far more common, is turbulent flow, chaotic, churning, swirling, like a tap on full blast. In turbulent flow, the fluid does not move in neat layers, characterized by random eddies, vortices, fluctuations in velocity in all directions. The bulk fluid moves forward down the pipe. Individual particles dart sideways, darting up, darting down, causing extensive mixing. To determine whether a flow is laminar, turbulent, or in the unstable transitional zone, engineers use a dimensionless number called the Reynolds number, abbreviated as Re. This powerful number provides a ratio that compares inertial forces to viscous forces within a fluid. Inertial forces relate to the fluid's momentum, its tendency to keep moving. Viscous forces are the internal frictional forces, the fluid's stickiness. A high Reynolds number means inertial forces dominate, leading to chaotic, turbulent flow. A low Reynolds number means viscous forces dominate, keeping the flow smooth and laminar. The Reynolds number combines four key variables: density of the fluid, average velocity of the flow, internal diameter of the pipe, dynamic viscosity of the fluid. The formula, Re like RHO VD MU. For a fluid like water, density and viscosity are known and change with temperature. Pipe diameter is a fixed design parameter, so Reynolds number is primarily driven by flow speed. Increase velocity, increase Re, eventually push from laminar to turbulent. Experiments give clear thresholds for circular pipes. Re below 2300 indicates laminar flow. Re above 4000 is considered fully turbulent. Between 2300 and 4000 is the transitional zone, avoided in design for unpredictability. Once we have used the Reynolds number to identify the flow regime, we can begin to calculate the energy loss to friction. These losses are categorized into two types: major losses, minor losses. Major losses are those that occur due to friction along the entire length of a straight pipe. They are called major because in systems with long, straight runs of pipe, they typically account for the vast majority of the total energy loss. Think of a long-distance oil pipeline stretching for miles or a water main running under a city street. The friction acting over these great distances is the primary obstacle the pumps must overcome. To quantify these major losses, engineers use a cornerstone formula in fluid dynamics, the Darcy-Weisbach equation. Despite its formal-sounding name, the equation is built on a very intuitive physical concept. It states that the head loss due to friction, H sub L, is proportional to several logical factors. First, it is proportional to the length of the pipe. L. Second, it is inversely proportional to the diameter of the pipe. D. Third, it is proportional to the square of the flow velocity, v squared. The complete Darcy-Weisbach equation is written as H sub L equals F times L over D times v squared over 2g, where g is the acceleration due to gravity. The term v squared over 2g is known as the velocity head, representing the kinetic energy of the fluid. The term L over D is a geometric factor representing the relative length of the pipe. The final and most crucial component of this equation is F, the Darcy friction factor. This dimensionless number encapsulates all the complex physics of the friction at the pipe wall. Calculating the friction factor EOF for turbulent flow when Re is greater than 4000 is significantly more complex than for laminar flow. This is because, in a turbulent state, the friction is not just a function of the Reynolds number. It is also heavily influenced by the physical roughness of the pipe's inner surface. A brand new smooth PVC pipe will generate far less turbulence and friction than an old corroded cast iron pipe of the same diameter. To account for this, we introduce the concept of relative roughness, which is the ratio of the average height of the roughness projections on the pipe wall, epsilon, to the internal diameter of the pipe, d. This ratio, epsilon over d, is a critical parameter for turbulent flow. The relationship between the Reynolds number, Re, the relative roughness, epsilon over d, and the friction factor F is not a simple equation. It was mapped out through extensive and painstaking experiments, most notably by Lewis F. Moody in 1944. He compiled the data into what is now famously known as the Moody chart. This chart is a graphical tool that allows engineers to find the friction factor by locating the intersection of their calculated Reynolds number on the x-axis and their pipe's relative roughness curve. The Moody chart is an indispensable tool that visually represents the complex interplay between flow velocity, fluid properties, pipe diameter. While major losses account for friction over long, straight pipe sections, they are only part of the story. Any real-world piping system is filled with components that disrupt the smooth flow of the fluid. These components include bends and elbows to change direction valves, to control flow tees and junctions to split or merge streams, sudden or gradual expansions and contractions in pipe diameter. Each of these fittings forces the fluid to rapidly change its speed or direction, which generates additional turbulence and results in a localized energy loss. These are known as minor losses. Despite their name, in systems with many fittings and short pipe runs, minor losses can add up to be greater than the major losses. The most common method for quantifying minor losses is the loss coefficient method. Each type of fitting is assigned a dimensionless loss coefficient, K sub L. This K value represents how much turbulence and energy loss that specific component generates. For example, a sharp 90-degree elbow has a much higher K sub L value than a smooth sweeping bend because it forces the fluid to make a more abrupt turn. A fully open gate valve has a very low K sub L, but a partially closed globe valve can have an extremely high K sub L. Let's solidify these concepts with two brief examples. First, consider designing a system to pump 15 degrees Celsius water at a certain flow rate through 100 meters of new, 5-centimeter diameter stainless steel pipe. The system also includes two 90-degree elbows, one fully open gate valve. The first step is to calculate the Reynolds number. Use the water's properties. Use the flow velocity. Use the pipe diameter. This will almost certainly be well into the turbulent regime. Next, find the relative roughness, epsilon over d for stainless steel. Use Re and epsilon over d to get the friction factor, F, or use the Colebrook equation. With F, calculate the major head loss using the Darcy-Weisbach equation for the 100 ml length. Find the KL values for the two elbows. Find the KL for the gate valve. Sum them and calculate the total minor loss. Total head loss are major plus minor losses. That final number is the minimum head the pump must provide to sustain flow. Second example, design an air duct system for ventilation with a 25 cm plastic duct. Air is much less dense than water. Air is also much less viscous than water. That yields a very different Reynolds number, even at similar velocities.